Okay, notes 4.3, trigonometric functions on the unit circle. So when we began this chapter, we looked at trigonometric functions of acute angles in right triangles. But now we're actually going to superimpose or overlay those triangles onto a specific circle so that we can find exact values of certain angles. And the circle we're going to use is the unit circle where the radius is equal to 1. So we're going to graph the circle that we're talking about. If we have a unit circle, that's actually the equation x squared plus y squared equals 1. This is the equation for the unit circle. This has a center at the origin, 0, 0, and the radius is equal to 1. So it doesn't really matter if we have a circle of radius 1 or radius 2, so on and so forth. Because if we look at an angle, no matter what the radius is, the angle will stay the same. So we're going to focus on the unit circle to help us narrow down some of the exact values that we're going to use. Okay, so we're going to put ordered pairs on our unit circle of 1, 0, 0, 1, negative 1, 0, and 0, negative 1. So this would be our unit circle of radius 1. And this is what we're going to study. So the formula below rates angle measure to arc length, and we talked about this a little bit in 4.2 as well. So the angle measure we know, which we call theta, is a ratio of the arc length s to the radius r. So what we learned was that theta was equal to s over r. And we also learned that theta, the whole way around the circle, is equal to 2 pi. But now let's look at this. If I solve this for s, I would multiply both sides by r. And so another relationship that we can see is this one right here, that the arc length is equal to the radius times theta. Well, in our circle, our radius is 1. And what that means for us is that our arc length and angle measure are going to be equal. So if radius is 1, we know that the arc length is equal to theta, our central angle. Okay, so in the next part of the notes, we're going to look at where these special angles and ordered pairs come from, or the value of these ordered pairs come from for our special angles in 3 situations. So in each situation, we're going to look at the first triangle. We're going to label the pattern for the special right triangle. The second triangle, we're going to adjust the sides so that the hypotenuse is equal to 1. And then we're going to draw and label the triangle onto the unit circle and find the requested trig ratio, which is the example at the very end. Okay, and we're going to do this for the next 3. So the first special angle we're going to look at is our special right triangle with pi over 4, which is 45 degrees. So that relationship we know is x to x, and the hypotenuse is x root 2. So that's the pattern. The second thing they want us to do is adjust the sides. So we want the hypotenuse equal to 1 on this second triangle. And this represents a radius on the unit circle. And we'll see that as we overlay it onto the circle at the right. So if I want 1 as my hypotenuse, I'm going to solve for x. So I'll let 1 equal root 2 times x, divide by the square root of 2. And so x is equal to, now I've got to rationalize that. So x is root 2 over 2, which means those are the side lengths of the other 2 legs. Okay, so now we're going to superimpose or overlay that angle onto our unit circle. So there's my 45 degrees, or my pi over 4. And we're going to make a right triangle. So from the top, we're going to come straight down and make a right angle. I know we don't go all the way to the edge of the circle down there, but that's okay. And what we're looking for is this point on the unit circle, this location. We want an ordered pair for that. So let's think about this. Now that we have our unit circle, we know the value of the hypotenuse is 1. And when it's 1, the relationship to x and y is that y is the square root of 2, and x is the square root of 2. And by x and y, I mean, I put a 3. And by x and y, I mean the base and the height of that triangle. So now, if we do look at this and we want an ordered pair, how do we get to this point up there? Well, the x-coordinate for the point would be that distance, root 2 over 2 on the x-axis, and then the y value, how far we rise to get to that point, which is also the square root of 2 over 2. So this particular point on the unit circle is root 2 over 2, root 2 over 2. Okay, so now we're going to find the sine of pi over 4. Well, I know that sine of theta is the opposite over the hypotenuse. So if I look at this triangle in particular, the opposite of theta is root 2 over 2, and the hypotenuse is 1. So I can reduce that to the square root of 2 over 2, and that will be the value for the sine of pi over 4. Okay, let's look at the next circle. So in this one, we're going to look at pi over 6, which hopefully we're now catching on, that's 30 degrees. So pi over 6, the relationship with pi over 6 is that opposite the 30-degree angle is x, opposite the 90-degree angle is 2x, and then the one left over opposite the 60-degree angle is root 3x, or x root 3. Okay, so we've labeled the relationship. Now we want to make the hypotenuse 1, and we want to solve for x so we can get the length of the other two sides. So if I have 1 equal to 2x, hypotenuse to hypotenuse, then x is going to have a value of 1/2. So when I substitute those in, that means that opposite pi over 6, this is a value of 1/2, and that opposite of the 60 is 1/2 times the square root of 3, or we're going to clean that up and write it as root 3 over 2, half of root 3. Okay, so now that we have those values with a radius of 1, we're going to write and superimpose this angle onto our unit circle. This is for pi over 6, or 30 degrees. I know that the hypotenuse is 1, this side is 1/2, and this side is the square root of 3 over 2. So I want this point right here. The ordered pair, the way that I get to that point will be to go the square root of 3 horizontally. So there's my x value, and 1/2 vertically. So that ordered pair is the square root of 3 over 2 and 1/2. And then the example they want us to look at is to find the tangent of pi over 6. Well, the tangent of pi over 6, we know that the tangent of theta is always opposite over adjacent. So if I look at pi over 6, the opposite is 1/2. The adjacent is root 3 over 2. So in this case, I'm dividing fractions. That would be the same as multiplying by the reciprocal, in which case the 2's would cancel, and I would be left with 1 over the square root of 3, and I would have to rationalize that to be root 3 over 3. And that will always be the tangent of pi over 6, or 30 degrees. Okay, then we're going to go to C. This is the last one, and of course we're going to look at the 60 degree. That's the one we haven't checked out yet. So opposite the 60 degree, we know is our root 3x, or x root 3. Opposite the 30 degrees is x, and opposite the hypotenuse is 2x. So once again, if I want my hypotenuse to be 1, then 1 equal to 2x, x is 1/2. So I know that this is 1/2, and this other side is root 3 over 2. And now we're going to superimpose that onto the unit circle. There's my pi over 3 angle. We're going to make a right triangle out of this. My hypotenuse is 1. This side here is root 3 over 2, and this side is 1/2. pi over 3, sorry. Okay. So now the ordered pair up here comes from a horizontal distance, or x value, of 1/2 and a vertical distance of root 3 over 2. Okay, the cosine of pi over 3 would be the cosine of 60, and we know that cosine of theta is equal to adjacent over hypotenuse. So for this case, we would have adjacent, which is 1/2, over a hypotenuse of 1, so the cosine is just 1/2, and that will always be the cosine of 60 degrees. Okay, so now, based on the patterns that we've seen from labeling those triangles, we're going to make some generalizations that will carry us through a lot of this material based on what we just did. So we're going to use x's, y's, and 1's to generalize some of these trig functions. So, trigonometric functions on the unit circle, let t be any real number on a number line, and p, being point xy, be the point on t when the number line is wrapped onto the unit circle. Then the trig functions of t are as follows. So really we can think of t as being our angle. That's our theta. So the sine of t, if we go back up and look where we did the sine was the opposite over the hypotenuse. And on the unit circle, the hypotenuse is always 1, always. So the opposite is always going to be that y value, that height, right there. So if I, oops, didn't mean to do that. So if I take root 2 over 2 and always put it over 1, it's always going to be root 2 over 2, or the y value. So what we can generalize from that is that y over 1 is always the sine on the unit circle. And we can simplify that to just y. So the sine of t correlates with the y coordinate. The cosine of t, when we looked at cosine of pi over 3, cosine is always adjacent over hypotenuse, always. And when we look at the unit circle, that's always going to be the x coordinate over 1. So we can associate cosine with the x coordinate. So I can say that the cosine of t is x over 1, and that it's just x when simplified. When we look at tangent, we saw that tangent, and we know that tangent is the opposite over the adjacent. So when I'm looking at theta, it's going to be the opposite always over the adjacent, and that is always going to be my y coordinate over my x coordinate. So I can say, in general, the tangent of t is y over x. So now I can look at the reciprocal functions. The cosecant of t, that is the reciprocal of sine, so that would be 1 over y. The secant of t would be the reciprocal of x, so 1 over x, and the cotangent of t would be the reciprocal of tangent, so that would be x over y. Okay, now we're going to use those going forward here in just a minute. First, we're going to make a quick stop with the angles on the quadrants when the points are on the axes. So these are called quadrantal angles because they are made up of the perpendicular intersection of the x and y axis. So we're going to label the 4 points on the circle on the x and y axis. So we have 1, 0, we have 0, 1, -1, 0, and 0, -1. So the angles at these points do pose a challenge because you can't draw acute angles with them. So what's cool about what we just did is the locations still have x and y values. That's all still useful. So we're going to use our new rules to find the values of these trig ratios. So as we look at example B, we want the exact value of the cosine of pi. So the cosine of pi, we just learned that cosine of theta can be related to as x. So if I look here at where pi is, my x-coordinate is -1. So the cosine of pi is -1. And that will always be true. Tangent of 3 pi over 2. We just related the tangent of theta to being y over x. And if I go look at 3 pi over 2 down here, my y over x would be negative 1 over 0. Now I'm not allowed to have 0 in the denominator, so the tangent at 3 pi over 2 is undefined. It actually doesn't exist. Okay, then we have secant. The secant is the reciprocal function for cosine. So 1 over the cosine of 4 pi is the equivalent of that, and then we're going to look at the cosine of 4 pi. So if you look with me at this unit circle, let's remember that halfway around is pi, and then the other half is 2 pi. And if we keep going around, we can count by pi's. So 5 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So our even pi's are over there at 1, 0, and our odd pi's are over there at negative 1, 0. So the cosine of 4 pi is going to be right there. And so cosine is the x-coordinate, so it will be 1 over 1, which is just 1. So the secant of 4 pi is 1. Okay, so now we're going to take a look at what we call reference angles. Okay, so trig functions on the unit circle, again, we're going to work in, we have just finished working in quadrant 1 and on the axes. So now we know everything we need to know about the first quadrant. But now we need to look at expanding because these angles can rotate through any of the quadrants. So we're going to use something called reference angles to make our lives much easier. Okay, quadrant 1, say that this is my theta. In quadrant 1, my theta and what we would call theta prime are equal. So reference angle rules right here. Theta is an angle in standard position. Its reference angle, theta prime, is any angle between 0 and 360 or 0 and 2 pi defined as follows. So we're looking for another theta value and we want to measure it from the x-axis. So when you're in the first quadrant, there is no reference angle, it's the angle itself. But let's say we move into quadrant 2. Now we have a theta value that goes into the second quadrant. Well, if we go into the second quadrant, a reference angle is going to be referred to as the distance from the x-axis to that terminal side. And the way that we would find that is we would take 180 and subtract that theta. So let's just use a number as example. Let's say this was 150 degrees. Well, the reference angle would be 180 minus 150, so that would be a 30-degree reference angle. And 30 is one of our special angles, and that we're going to find that happen a lot. We're going to have the special angles show up. That's what we're going to work with. Now, if we were in radians, we would take pi minus theta to get the reference angle. If we're in quadrant 3, so my theta value comes all the way over here. Let's say, just for example, that my angle is 225. Well, my reference angle says how far are you from the nearest x-axis, and that is this value right here. So here is where, to find the distance away, we would take theta, or my 225, and subtract 180. In this case, it would be 45 degrees. So 45 would be my reference angle. If I put my angle in quadrant 4. So here's my theta all the way around. But my reference angle is going to be, again, the distance to the nearest x-axis right there. So let's say my angle is 330 degrees around. That's my theta. My reference angle would be 360 minus that theta. So it would be, 30 degrees. So my reference angle would be 30. Okay, so as we work with reference angles more, and as we label the ordered pairs on the unit circle, that's going to make more sense. So if you're feeling a little fuzzy on this right now and wondering what are we going to do with these, just stay hooked. It's all going to come together. Remember the reference angle, okay, is always formed with the nearest x-axis. Okay, and reference angles are always positive. And the reason is they are a distance from the x-axis. So on the circle below, we're going to draw and label with both degrees and radians a 30-degree angle, which is also pi over 6, and we're going to draw and label angles in the other 3 quadrants that have the same reference angle. So we're going to get started with, first of all, our 30 degrees. So here's my initial side, and we'll put a terminal side right there. So that represents 30 degrees, or pi over 6. So if we want a reference angle in the second quadrant of 30 degrees, draw a different color, we're going to put it over here. This might be how big? Well, if this is a 30-degree reference angle, this whole angle must be 180 minus 30, or 150 degrees. If we're in radians, think about the fact that all the way around would be 6 pi over 6. All the way around, just half a circle is what I mean. So halfway around the circle would be 6 pi over 6. But I am pi over 6 shy of being halfway around. So if I take off that pi over 6, realize that I am at an angle from the initial side of 5 pi over 6. Then if we put one in the third quadrant, reference angle of 30. So 30 away from the x-axis. In degrees, we would take 180 plus 30. And so this angle would be 210 degrees, again, from the initial side all the way around. And as far as radians, we've gone 6 pi over 6, halfway around, plus another 30 degrees, or pi over 6. So this angle in radians would be 7 pi over 6. Then, in the fourth quadrant, reference angle of 30 degrees. This would be all the way around, would be 330 degrees to have a reference angle of 30, so that it's 30 away from the full revolution. All the way around would be 2 pi, or 12 pi over 6, since we're in sixths. But if I am pi over 6, or 30 degrees shy of that, that whole angle is 11 pi over 6. Okay. So now maybe the murky waters of reference angles are clearing up just a little bit. Don't worry if they're not. If it's still fuzzy, we're going to work with them a bunch. So sketch each angle and find, now we're just going to find its reference angle. So the first we have is 300 degrees. So 300 degrees would be in, think about what quadrant. It would be beyond 270, not quite 360. So it's over here in the third quadrant. So that's, fourth quadrant, that's 300 degrees. The reference angle is the distance to the nearest x-axis. So 360 minus 300 gives me a 60-degree reference angle. Okay. Then I have negative 2 pi over 3. The negative just means we're going to rotate in the other direction, but think about where you are. This all the way over here would be negative 3 pi over 3. Well, we don't get that far. We only get to negative 2 pi over 3, so we're going to be here in the third quadrant. So if I went all the way around, I would have been at negative 3 pi over 3, but I am pi over 3 shy of halfway around the circle. So my reference angle is pi over 3. Okay, so that's how we find a reference angle. How far away from the x-axis are we? Have we gone over it or not quite got there, but it's a distance from the x-axis? Okay, so at this point, I want to go to the unit circle, this big unit circle that you have right here. I don't know if I can shrink that enough. Okay, so looking at this unit circle now, we're going to label all the way around the unit circle with our ordered pairs. So what we have already done, and you don't have to scroll back, but I want you to just look. We went all the way through and proved how we got the ordered pairs for the first quadrant, for the 30, 45, and 60. We showed how you can get those answers or those values from the right triangles. So now we're going to look at carrying them through what we know about reference angles. We're going to carry them through the whole unit circle. So I'm going to show you how to label this. We're not going to regenerate all the triangles, but I'm going to show you a method that makes it super quick and super easy. Not really cheating, but it's not anything you might see in a math textbook. You might find a quick video doing the same thing on YouTube or something. But here's what we're going to do to know all of the ordered pairs. We're going to first go around and put parentheses at every point. And there's actually another video on my Canvas page with someone else doing this. So knowing this unit circle is going to help us find degree measures and exact values of these trig functions and the angles all the way around the unit circle. Okay, first thing we're going to do is label the quadrant angles, or the quadrant points. So we know this is 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Okay. All right, the next thing we're going to do is we are going to go to each one of these parentheses and we are going to put divided by 2, divided by 2, divided by 2, all of them. That would be the end of C lunch. Okay. Okay, so now the next thing we're going to do is we are going to go put square roots in all of the numerators. Yes, all of them, like this. Square root, square root, square root, square root. Okay, so we're going to start with the x's, and as long as you can count to 3 and back down, you're going to be great. With the x's, we start at 3, and we are going to go around the circle. 3, 2, 1, 1, 2, 3. 3, 2, 1, 1, 2, 3. So here we go. 3, 2, 1, 1, 2, 3. Staying in the x coordinate. 3, 2, 1, 1, 2, 3. Now we're going to do the y's, and we're going to go in the other direction. 1, 2, 3, 3, 2, 1. 1, 2, 3, 3, 2, 1. Just like this. 1, 2, 3, 3, 2, 1. 1, 2, 3, 3, 2, 1. Okay, so now there's something we do need to adjust real quickly. We're going to do the signs here in a second, but the square root of 1 is just 1. Do not leave it as the square root of 1. So I'm going to go and erase all of my square root symbols when it comes to 1. And as you do this, you'll learn not to put the square root there when it's 1 if you want. Either way. Or you may do the numbers first. Maybe you want to do the numbers first and then do the square roots second. And so then when you have a 1, just don't put the square root there. So, okay, now we have the ordered pairs almost. But we have to remember that we are on also the x and y axis because we do have x and y ordered pairs. So we need to think about signs. When we're in the first quadrant, guys, we always have, why am I missing some parentheses? Okay. We always have an ordered pair that would be positive x and a positive y in the first quadrant. Positive, positive. So nothing needs to change on those ordered pairs. When you move into the second quadrant, in the second quadrant, our x's are negative and my y's are positive. So you have negative x's and positive y's. So now we just need to make the x coordinates negative. We're going to look at the third quadrant. In the third quadrant, you have negative x's and negative y's. So we're going to go in and make each x and y negative. And in the fourth quadrant, we have positive x's and negative y's. So we're going to go make those negative. The y coordinates negative. Okay, so there is your unit circle with all of the ordered pairs and their signs. And we're going to use this to determine values of angles with sine, cosine, tangent, and secant, cosecant, cotangent all the way around the unit circle. So let's go back now. Oh, actually, before we do that, let me point something out. Right here. As you know, when we move around the unit circle, as we just saw, we have sign changes in x's and y's. So I'm going to teach you a little trick about remembering where trig functions are positive. Okay, so this little trick is just to tell us where trig functions are positive. So it goes like this. Start in the upper right-hand quadrant, quadrant 1. Always study trig carefully. Always study trig carefully. And what that stands for is all of the functions are positive in the first quadrant. Only sine is positive in the second quadrant. Tangent is positive in the third quadrant. And cosine is positive in the fourth quadrant. So this is where the trig functions are positive. So in other words, tangent and cosine are going to be negative. In the third quadrant, sine and cosine are going to be negative. And in the fourth quadrant, sine and tangent are going to be negative. So always study trig carefully. Helps us to remember, because one of the big things is to know your location of your angles. That is huge, guys. So let's start with A, the sine of 150 degrees. Let's see where this is. 150 degrees would be in your second quadrant. So here's 150. What we're going to do is use the reference angle. So it is 30 degrees away from 180. So my reference angle is 30 degrees. If my reference angle is 30 degrees and I want the sine function, so the sine is going to be positive in the second quadrant. What I can do is I can go to my unit circle and look right here at 150 degrees. The sine is the y value, and that is 1/2. So the sine of 150 is the same essentially as the sine of 30, which is 1/2. The cosine of 7 pi over 4. Where is that? So 7 pi over 4 is really close to 8 pi over 4, which is 2 pi all the way around the circle. So 7 pi over 4 is down here in the fourth quadrant. So my reference angle is pi over 4. So the cosine in quadrant 4 is going to be positive. So now I want to know the cosine is related to x. So let's go look at pi over 4, or 45 degrees as a reference angle in the fourth quadrant. And that's going to be my x value, and that's the square root of 2 over 2. So that would be the value of the cosine of 7 pi over 4. It's the square root of 2 over 2, because it's just the x coordinate. The tangent of 2 pi over 3. So 2 pi over 3, if we think about where that is, that's going to be in the second quadrant. The reference angle would be pi over 3, away from 3 pi over 3. So when we look at tangent, remember tangent was y over x. So let's go to 2 pi over 3, or pi over 3 back, and that's going to be right here. And we're going to put y over x. So root 3 over 2 over negative 1/2. So root 3 over 2 over negative 1/2. We know that in quadrant 2, tangent's going to be negative, so it makes sense that we have a negative value in there. Then my 2's are going to cancel, and I'm left with negative root 3 over 1. And there's my value. Okay, now we're going to look at the secant of 330. So first, location, location, location. The secant of 330, this is going to be in quadrant 4. So we have an angle down here of 330 degrees. My reference angle is 30 degrees. So secant is the reciprocal of cosine. So let's look at the cosine. What is the cosine of 30? In the fourth quadrant, cosine and secant are actually going to be positive. Secant is just the reciprocal, so it's going to have the same sign. So let's go to the unit circle and look at 30 degrees in the fourth quadrant, which is right here, and it's going to be that x value, root 3 over 2. So root 3 over 2 would be the cosine of 30. But remember, we want the secant, so we're going to flip that. 2 over root 3, and then rationalize. 2 root 3 over 3 is our value. And it is, again, in the fourth quadrant, so it's positive. Okay, the sine of 4 pi over 3. So where is 4 pi over 3? Well, 3 pi over 3 is halfway around, so 4 pi over 3 is going to be right here. The reference angle is going to be pi over 3. It is pi over 3 units more than 3 pi over 3. So if I look at the sine of 3 pi over 3, let's go to the unit circle. Pi over 3, the sine is the y value, and that's negative 1/2. So negative 1/2. Good. The sine of 3 pi over 2. Well, 3 pi, we know that the sine is related to y. 3 pi over 2 is right down there at 270 degrees, and we're just looking at the y values, so the sine of 3 pi over 2 is negative 1. The tangent of 150. 150 is in quadrant 2. Tangent in the second quadrant is negative. So it's going to be negative something. So here I am. There's 150 degrees. My reference angle is 30. So I'm going to look at 30 as a reference angle in the second quadrant. And tangent is y over x. So I would have 1/2 over root 3 over 2. And that's negative. So let's go back up and simplify that. 1/2 over negative root 3 over 2. So that reduces to a negative 1 over root 3, and as I rationalize, that is going to be a negative root 3 over 3. Okay, and lastly, the secant of 15 pi over 4. Wow, 15 pi over 4. So the very closest to halfway around or all the way around, if we count by pi's, remember, how do we know where this is? So watch closely. If we do 15 pi over 4 is close to 16 pi over 4, right? 13 pi over 4, 14 pi over 4 is not an integer. We want integers so that we're on pi or 2 pi, right? Because this is 1 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi. So we want integers of pi, and the closest integer, the closest number that would give me an integer would be 16 pi. The other one would be 12 pi over 4, or 3 pi, and I'm definitely closer to 16. So 16 pi over 4 would be 4 pi. That's 2 full times around the circle. But 15 pi over 4 doesn't quite make it. So 15 pi over 4 would actually be in the 4th quadrant. It would be how many times around? It would be 1 full time around is 2 pi, and almost another. So 8 pi over 4, the next would be 16 pi over 4, but we only make it to 15. So the reference angle is pi over 4, and the angle has a terminal side in the 4th quadrant. Now, secant is the reciprocal function of cosine. So if we think about the cosine of 15 pi over 4, well, think about the reference angle, the cosine of pi over 4. Let's go there. Cosine in quadrant 4 is going to be positive. So let's go to the 4th quadrant with a reference angle of pi over 4. It's right down here, and that's going to be our x value. So that would be root 2 over 2. That's cosine. So we've got root 2 over 2, but I want secant. So we're going to flip it. 2 over root 2, and then rationalize. So 2 root 2 over 2, the 2's cancel, and my final answer is just root 2. Okay. So hopefully that gives us a little more perspective on reference angles and how they're used. So we've been talking about the unit circle, radius of 1. Now what we're going to do is this: extend the principles of the unit circle to any angle in standard position in any quadrant of the coordinate plane. Okay, so now this means we can have something that is beyond a radius of 1 or less than a radius of 1, but again, that doesn't affect our angles. So we're going to let 2, 5 be a point on the terminal side of an angle theta. So let's draw this. Oop. Okay, so positive 2, positive 5 is going to be in the 1st quadrant. So we're going to draw this theta. 2, 5. There's theta. So 2, 5 is this point right here, which means that to get to that point, 2, 5, I had to go over 2 and up 5. So it's a point on the terminal side of an angle theta in standard position. Draw the triangle on the coordinate plane and find the exact values of the 6 trig functions. So we want sine of theta, cosine of theta, tangent, cosecant, secant, and cotangent. So I need to find the 3rd side, or the hypotenuse. So I'm going to do 2 squared plus 5 squared. is equal to c squared. So I get 4 plus 25 is equal to c squared. So c squared is 29. So I know that this hypotenuse is the square root of 29. Now I have all three sides of my triangle, and since I'm in the first quadrant, I don't have to worry about positives or negatives. So let's list the sine, cosine, tangent, and their reciprocals. So opposite over hypotenuse for sine will be 5 over the square root of 29, and we have to rationalize that, so that would be 5 root 29 over 29. The cosine is going to be the adjacent over the hypotenuse, so 2 root 29, or 2 over root 29, and when I rationalize, 2 root 29 over 29. The tangent would be opposite over adjacent, so 5 over 2. Now I'm just going to do the reciprocals. So cotangent is 2/5. And then for sine and cosine, being that they had the radical on the bottom, when I flip them and do the reciprocal, cosecant and secant, it's pretty nice. I would just have the square root of 29 over 5 and the square root of 29 over 2. So these, given a point on the terminal side, we label that triangle, and now I have the sides, and I can tell you all of the 6 trig functions. Okay, so then, theta is any angle in standard position. The point P, X, Y is a point on the terminal side, and R represents the non-zero distance from P to the origin. So here's what that means. R is the radius of that circle. So we're no longer saying that the radius is necessarily 1. The radius could be 5. The radius could be 1/2. So now it's not going to change drastically, but when sine of theta used to be y over 1, because 1 was the hypotenuse, now we have this. We have x, y, and r. So the sine of theta would be y over r. The cosine of theta would be x over r, adjacent over hypotenuse. The tangent is still y over x, nothing to do with the hypotenuse. And then the reciprocals. So the cosecant would be r over y, as long as y is not 0. The secant would be r over x, as long as x is not 0. And the cotangent would be x over y, as long as y is not 0. So let's practice some more examples. Now this first one is the exact one that we just did. So we're going to change this up to -2 and -5 instead of 2, 5. We just did that one. So think about where this is. Let the following points lie on the terminal side of an angle theta in standard position. Find the exact values of the 6 trig functions. So let's see. -2, -5 is going to be in the third quadrant. So if I make the triangle, now guys, make the triangle with the x-axis. Theta is always with the x-axis. So -2 is my x value, -5 is my y value. Hypotenuse is always positive, and I'm going to have the same hypotenuse as I did in the previous example, the square root of 29. 2 squared plus 5 squared is 29, and the square root of that. So now we have this labeled. So sine of theta, cosine of theta, tangent of theta, and then cosecant of theta, secant of theta, cotangent of theta. Now, if you remember, always study trig carefully. We're here in the third quadrant. The only thing positive will be tangent. So I know right now that sine and cosecant are negative, and cosine and secant better be negative. And we'll see that as we look at our ratios. So sine would be opposite over hypotenuse. So it is going to be -5 over the square root of 29, which does rationalize to -5 root 29 over 29. The cosine would be negative 2 over the square root of 29, which rationalizes to negative 2 root 29 over 29. And the tangent will be opposite, which is negative 5, over adjacent negative 2. And of course, that's a positive 5/2. So as we look at the reciprocals, cotangent would be 2/5. The secant would be negative root 29 over 2. The sine would be negative root 29 over 5. And there we have all of our 6 measurements, or 6 ratios. Okay, now we're going to do B, where the terminal side of an angle has the point negative 4, 3. I would tell you guys to pause the video and try this one on your own, and then check and see if you get it right. Okay, negative 4, 3 is going to be in the second quadrant. Again, make that theta with the x-axis. Negative 4 is your x, 3 is your y. So if I find the side, we have a 3, 4, 5 right triangle. So the hypotenuse with Pythagorean theorem would give me 5. So let's go find the sine of theta, cosine of theta, tangent of theta, cosecant of theta, secant of theta, cotangent of theta. And keep in mind, always study trig carefully. The only thing positive, we're in the second quadrant, the only thing positive will be the sine function. So I know that sine and cosecant are positive, but cosine, secant, tangent, cotangent are all going to be negative. Okay, so the sine opposite over hypotenuse will be 3/5, and the cosine or cosecant will be 5/3. The cosine adjacent over hypotenuse will be negative 4/5, and the secant will be negative 5/4. The tangent will be opposite over adjacent, so negative 3/4, and cotangent negative 4/3. Okay, good. Almost there. So this is going to just bring together what we just talked about. This is my little always study trig carefully. It kind of breaks it down. So let's just look at the signs once again. Finding trigonometric values of angles. We pointed out it's important to know whether the value will be positive or negative. So we're going to take another minute and label where the different functions are positive and negative. So if we are looking at sine and cosecant, then we have, now these are skewed. So sine and cosecant is this, cosine and secant is this, and tangent and cotangent is this one. So sine and cosecant are going to be positive in the first and second quadrants, and they will be negative in the third and fourth. Cosine and secant are going to be positive in the first and the fourth, because that's where x is positive, and negative in the second and third. That's where x is negative. Tangent and cotangent, they will be positive when you are in the first and the third, because that's where you have 2 positives or 2 negatives, and then they will be negative in the second and fourth. So here it is, and I gave it to you prematurely, but I really felt like it was helpful and it was a great opportunity to get to use it. So here it is again. Always study, which stands for sine, trig, which is for tangent, carefully. And that's for cosine. There's another saying, all students take calculus, but that's just not true. So I go with this one. This is always true. You do always have to study trig carefully, and the always stands for all. Okay, let's do an example application. So robotics. You have a student programmed a 10-inch long robotic arm. So this robotic arm right here is 10 inches long. Initial side, there it is labeled, 10 inches long. And we see that it's rotated. it's going to pick up an object at point C, right here at the initial position, and rotate through an angle of 150 degrees. In order to release it into a container at point D, we need to find the position of the object at point D right up here relative to the pivot point 0. So in other words, I want to know the location, the ordered pair for that. So we can use trig to do this. Now you can go back to the unit circle, but look at this. If I make that horizontal and extend it so that all the way around is 180, here's what I have. I have a 30-degree reference angle right in there. And so I know that if I go and look, if this is 10, then I know that opposite the 30, so if this is 10, opposite the 30 is 10 divided by 2, and that is going to be 5. And I know that opposite the 60 is going to be x root 3, which is going to be 5 root 3, and it's negative. So the location would be, and again, your unit circle is just that when your radius is 1. But this actually, if we made a circle, has a radius of 10. So knowing the relationship for the 30, 60, 90 is still critical. Opposite the hypotenuse is 10, or I'm sorry, 2x. So again, not forgetting this relationship we have. This is 2x, x, because this is 30, and this is 90. And then we have x root 3. So if I know that that's 10, then x has to be 5, and this has to be 5 root 3. So my position is negative 5 root 3. Need a little more room. Negative 5 root 3 and positive 5. So if we round, I'm not going to round it to the nearest tenth, I'm just going to leave it as that. So the point, the position, is negative 5 root 3 inches by 5 inches, and that would be the location. Okay, so a few more. This is just extra practice, so this is nothing new. We're going to work on our location and our signs and our values. So we're going to sketch each angle, find the exact value of the expression, and we might need to make more than one revolution. So this is good too, to look at breaking it down into how many rotations we have. But keep in mind, the process is the same. So we have 9 pi over 4. So if I want an integer, 1 pi or 2 pi, the closest to that would be 8 pi over 4, which is below it, or 12 pi over 4, which is above it. So 8 pi over 4 is the closest. So I'm looking for 8 pi over 4 would be 2 pi all the way around. And then 1 more pi over 4 puts me right there. Now, I'm in the first quadrant, so my reference angle is pi over 4. So the cosine of pi over 4, if we look at that as a right triangle, opposite of the pi over 4, you can go back to that unit circle. Pi over 4 right there in the middle, is your x value is going to be root 2 over 2. So my value for the cosine of 9 pi is root 2 over 2. Just the x-coordinate for that point. Okay, the sine of 300. So the sine of 300, if we think about where that is, I'm going this way. There's negative 90, negative 180, negative 270. Negative 300 is somewhere in quadrant 1, so it's going to be positive. My reference angle is going to be 60 degrees. So if I think of the sine of 60 degrees, I can go back to my unit circle. 60 degrees. The y value is my sine, so that's root 3 over 2. And it's positive because I'm in the first quadrant. Okay, so the tangent of 29 pi over 6. So again, try to make an integer. I can do 30 pi over 6, which is a little more than that. And then below that would be, I guess, 24 pi over 6. 24. So I'm definitely closer to 30. So 30 pi over 6 would be 5 pi. All right, look at this. So 1 pi, 2 pi, 3 pi, 4 pi, 5 pi would be 30 pi over 6, but I didn't get all the way to 30 pi over 6. I only got to 29 pi over 6. This puts me in the second quadrant. So watch that again. 29 pi over 6. If I want an integer of pi, 1 pi or 2 pi, the closest is 30 pi over 6, which is 5 pi. I didn't quite get there, but let's see where we are. So there's 1 pi, 2 pi, 3 pi, 4 pi, almost 5 pi, but I am pi over 6 shy of getting to 5 pi, or 30 pi over 6. So this has a reference angle of pi over 6, which is 30 degrees. Now this is tangent, and it's in quadrant 2. It's going to be negative, so negative something. Only the sign is positive in the second quadrant. So if I go back and look at my unit circle for pi over 6, or 30 degrees, tangent is y over x. So 1/2 over negative root 3 over 2. Where am I? So we have 1/2 over negative root 3 over 2. The 2's cancel. Negative 1 over root 3, when I rationalize, is negative root 3 over 3. And that is the tangent of 29 pi over 6. Okay, so a lot in this section. I would encourage you to review it if you need to.